So cloud fitness engineering is primarily how do we implement cloud? How do we drive cloud implementations that are aligned to business outcomes, that maximize business outcomes? Now, why we need this is, I work in Accenture, and we did a survey, and we found that more than 30% of the organization, which adopted cloud, either native or migration, did not find the business benefits. Technically, everything would have gone on well, but they did not find business benefits. So, what is required for us to, how do we implement business goal aligned cloud, applications or the whole ecosystem, right? So, if you look at the SRE document by Google, it's so comprehensive. If you read the document, it has elements of design, elements of architecture, elements of coding, elements of course, the production support. It's so comprehensive. So often we wonder whether one single role can have all these skills. So what is required is to deconstruct the role of SRE and synthesize those activities in the larger life cycle, A, and B is how do you complement upstream activities with SRE roles? Why do we need to do it? Is to ensure that the business outcomes are aligned to all these activities, and these activities are aligned to the business outcomes, right? Now, if you look at the current, we call now the rise of platform economy, right? Because every company, whether product company or service company, is reinventing itself as a platform company. You start with Uber or Airbnb, but then now there are more and more, right? Platform is primarily putting all stakeholders together to drive innovation, drive productivity, and drive cost control. Now, what we see is cloud is the business. Cloud is the essence and core of the business strategy, and cloud shapes the business strategy. Important to ensure that the business outcomes are realized when we implement cloud, and we also understood that many organizations do not seem to realize the business outcomes. So what is required for us to ensure the business outcomes are met, right? And with the rise of platform economy, it's more important that, because the cloud is the business model, the technical capabilities of the cloud platform has to be aligned to the business goals. So, and the technical capabilities primarily are all the so-called non-functional or behavioral aspects. And what influences technical capabilities are the design architecture decisions. The business aligned. So the design and architecture decisions have to be aligned to the business goals. Now we'll examine what is the challenge in ensuring this, right? And second is, with the rise of platform economy, it's also important that the platform adapts itself with the changing business vision and goals, because business goals change, the vision changes, the technical capabilities have to be aligned with the business goal. Now, what happens to the decisions that are taken while architecting the cloud, right? Now, the key challenge is cloud is distributed, heterogeneous, asynchronous, message driven, event driven. It exhibits a high degree of uncertainty. Cloud is a world of VUCA. Volatility, variability, uncertainty, complexity, and very ambiguous. And the failures are very unpredictable. Every time you figure out, oh, this is a pattern of failure, then that pattern doesn't appear. Something else appears. And what are those typical issues? You have those DNS issues or upgrade issues or automation scripts, going haywire. And why they happen? Some examples. Cloud being, you have your concurrency and parallelism. There are, race conditions and deadlocks. Clocks, often distributed system, clock syncing is a problem causing mismatch. Then scalability, as you add resources to make a cloud application workload scalable, there's a point after which your scalability, increase of resources will not add to increased throughput or decreased latency, because there is something called the universal scalability law. More resources up to a point, you have scalability. Beyond a point, the resources, the communication between the resources actually can cause. So, non-linearity, I have not added that. It's non-linear, right? And if there are any faults somewhere, or if a node doesn't respond, does the requester assume that the node is down, or is the node plain slow? Those decisions, the actual core, the logic decisions. So if electronic load balancer is, certifying a server to be unhealthy because the server was slow, then if 2-3 servers are slow and then they are all marked as unhealthy, the healthy ones start to get all the load, and the entire thing goes into a cascade of failures. So cascading failures, concurrency, scalability. Now, example is during an upgrade, when the upgrade process flushed out the cache, and that caused the databases to be overloaded, which in turn prevented the cache to be refreshed, causing complete chaos. And then, if you read the Google SRE notebook, the book, there is a very interesting example of an application hosted on the Google application engine. One fine day, that application became very slow, and they tried to figure out, is it database, is it some server getting overloaded, whatever, nothing, right? They solved the problem temporarily by adding more resources. Right? Now, what was the reason? They found this reason after a few days, is that in the application logic, it has a whitelist. So if a request comes from a particular path, it creates a whitelist, and then that's okay. But then they had run a security scan process which kept sending requests through that path, and the whitelist grew. And we all know, as programmers, as architects, whitelist cannot grow beyond a point. The whitelist grew to a large size, and every time a request comes, it has to check the whitelist. So can you predict them? Uncertainty, VUCA, right? Do we accept the VUCA-ness? I don't know. If you look at this, because we lost time, this is a very interesting problem. You have a normal working system, then you have an observed fault based on observability or whatever you want to call. There could be 3 pathways. One is the failure pathway. Other could be there's a transient fault and no failures. Third could be a false alarm. And if you go wrong, in fact, you take action on a false alarm, that can cause problem. There is uncertainty in observability. We all say that AI can solve the problem, but there are false positives, false negatives, and then we try to answer that by saying that, lot of data is required, but how much data is required? The inherent uncertainty in observability. And the interesting thing is, the earlier you predict an adverse event, the more useful it is. But more unpredictable, more uncertain that prediction is. Like rain. Can you predict rain? It's going to rain in London this afternoon or this evening. In the morning, can you predict? If yes, it's more useful because you can plan your day, but it is more uncertain. Now, this is something that as architect community, as design developer community, as SRE community, as business folks managing all this, understand there's an inherent issue with prognosis and diagnosis, causal analysis. Often causality goes wrong. I think I'll recommend a book called The Book of Why by, I forget the name, the author indicates how it is difficult to establish a clear causal link in complex systems, because correlation is not causation. And then you could have confounders, you have coincidences. So often in observability, we do have problem with these, with uncertainty as a major issue. Now, so why so? Because the very characteristics of cloud that gives cloud business benefit also give rise to risks. If you read this, scalability comes because it is distributed and asynchronous, but the same reason give rise to distributed failures. Abstraction and automation are a big feature of cloud. It helps us being agile, but abstraction and automation can cause lack of visibility, lack of understanding of the operator. So similarly, you have all this, the very characteristics of cloud that gives us benefits also give rise to risks. And what are those risks? We'll come to that in a minute. So the design architecture decisions, and I'll come to it, testing or SRE decisions have to be taken under a great deal of uncertainty. I think as community, we have to accept that in distributed systems, uncertainty is a big problem. Now, what are these, the consequences or the design decisions context? Because a developer has to take, trade-offs. Trade-offs have to be performed, conflicts have to be resolved, constraints have to be understood. For example, for a particular application, you design for high throughput, latency could be affected. You design for, you have the CAP theorem, right? Consistency, availability, and partitioning. So anything you take here, there are consequences. And any design choice a developer makes has consequence. Whether choice of SQL, choice of RDS in AWS, or serverless versus server-based application, everything has a consequence. Now, and then, and developers and architects, they have no way of envisaging or forecasting the runtime consequences of what they do, what choices they make during architecture and design. So failures are unpredictable. So we say that embrace failures. I would say that's fine. Let's embrace uncertainty. Once you embrace uncertainty and then accept that uncertainty in distributed system is a main cause, a major contributing factor of platform enterprises or companies which depend on cloud not meeting their business goals or not realizing their business potential, then we can go on to understanding how to address the uncertainty, right? Now, what is the consequence? So you have value risk, means the company does not realize the value. For example, a hotel chain wants to ensure 30% of their revenue comes from partner portals. Now, what are the platform capabilities? How the platform has to adapt its behavior to be able to meet the business goal, or algorithmic trading. Anything you take, the value, the business value has to be defined, and there is a risk because of uncertainty. There is a risk that the value is not realized, and failures, distributed failures, and the cost is primarily cost, cloud resource usage, not commensurate with the business value that the application is providing. So three-pronged risk. Now, cloud fitness engineering is primarily architecting, implementing, running fit for outcomes cloud applications, addresses the VUCA challenge in cloud, and enabling lifecycle process and people collaboration. Now, what are the first principles? How do we address uncertainty in life, in career, or whatever, right? Let's not go into the technical part. First and foremost is systems thinking and cognitive skills. I think as community, we have to understand, appreciate the value of tools, but the human cognition, the cognitive skills are going to be important. And second is, there has to be a goal cascade from the business goal all the way down to, I'll explain that. And third is continuous modeling of behavior. Again, I will explain. Fourth is simulation experiments. I think one of the speakers spoke about simulation. Fifth is part A and part B is a control system in the process, so that we have a continuous feed forward and feedback. Like you drive a car, you're driving on the highway, your mind goes through a continuous control system. You know, you feed forward, you look at signs ahead, you look at traffic ahead, you predict, you fine tune your driving or your pathway, and then as you go along, you learn and apply the feedback into your subsequent drive. So let's take it one by one. Systems thinking, it's very interesting. Despite all the automation, there are flight accidents, and there are three main reasons why the flight accidents happen. One is situational awareness. The pilot doesn't have loses situational awareness, and second is a mental model of the outside environment and its connection with the dashboard and the controls. So first is situational awareness, second is a lack of mental model, and this is other related thing is be able to share that mental model with the co-pilot. It's not about dashboard, not about just observability, if you take analogy with SRE. And third is crew resource management. Once you have situational awareness, once you understand the mental model is perfect or near perfect, and you share that model with your colleague, next is to ensure that the team is allocating its tasks in a very balanced manner, right? Now, so cognitive skills, your memory, your perception, understanding, problem framing, pattern recognition, conceptualization, and these are going to be very important going forward when the platform economy takes off. More and more platforms will come into production. I think the system thinking and cognitive skills have to be, I would say, must be encouraged rather than just depend on tools. Tools are a means to enable thinking and decisioning. Right. The second is goal cascade and risk to goal approach. So here we propose that from the business outcome goals, which are primarily the balanced scorecard approach, revenue goals, customer goals, and internal outcome goals, you cascade these goals into service performance KPIs. Service, all your throughput, latency of every payment service flows, or a customer journeys, or a supply chain service flows. And from there, cascaded down to the trace performance goal. And this is not going to be easy because the sensitivity at every level of change, for example, what trace goal have to be defined to be able to meet a particular service performance KPI, and in turn, how the service performance KPIs affects business goal is going to be a matter of initial hypothesis, and we will see how to through simulations and modeling, and those decisions have to be traceable to the trace performance, the architecture trace performance goals. And you have all those frameworks like well-architected framework of hyperscalers, architecture decision records, and you have design patterns, So now this is the second point. First was system thinking and cognitive skills. Second is business success goals decomposed or cascaded all the way down to trace goals. And the trace goals, the trace goals, they are recorded in the architecture decision records. And now next is behavior models. There is so much talk about observability, rightfully so, but observability is still a lot of data. The observability data must be abstracted as behavior models. And we suggest, based on experience, three kinds of behavior models: failure models, decision consequence model, and cost benefit model. Failure modeling, Initial modeling is done through static analysis, which is component interaction analysis, and then you ask questions as a team. How will this architecture with these decisions tend to fail or degrade? Failure could be outright failure outage, or degradation could be for performance degradation, security issues, or cost degradation, right? Second is you have documented architecture decision and architecture decision records. Every decision you have taken, you have gone for serverless. What are the consequences? They have to be modeled. And third is a cost benefit, which is, what does it take? I mean, you have decided this. What are the cost benefits, right? Now, okay, I have done a modeling. Now, the modeling is still a static modeling based on my intuition and my judgment, based on the team wisdom. Obviously, next has to be a continuous simulation experiments. Now, these are not new. We understand performance engineering. We understand chaos engineering. Many of us have done chaos testing. So we put all this here. I don't want to call it chaos experiment, because chaos experiment, there is some association with pull down wires, remove, down the microservices and see what happens, right? Here is very thoughtful experimentation based on, proving those hypotheses here in a continuous loop. Now, what happens up to this point is your simulation experiments, which are conducted on a sandbox system, will be able to continuously update the behaviors, and from there you can update the architecture decisions and fine tune it to meet the business goals. It's a continuous experimental process. Now, the experimental setup here is, you have context stimulus, you have various loads, profile, combination of load and fault vectors, combination of threat vectors, fault vectors, and load vectors. And then you can have all those experiments. We call it the chaos, or the chaos kitchen. And then you check the internal response data. You can use the RED model or use model. I don't know how many of you have are familiar with those models. Use is utilization, saturation, and error. RED stands for rate, error, and duration. Those models can be applied to understand how the failures tend to happen, what are the runtime consequences of the design choices, and how the cost benefit is shaping up. Now, next is control system, right? Now, the control system, as we said, a control system is required to continuously feed forward and feedback, and then continuously fine tune in order to meet the business goals. Here, now we have a common model. Now, dev, QA, and SRE or ops, they have a common behavior model. They can talk and they can collaborate. The common shared mental model, right? Now, that what happens here, that feed forward here is, as development, as the dev people or the architects make a change, they feed forward that change to the QA teams, or they feed forward it to the SRE team, saying, look, I'm making a change here. There are possible consequences. Be aware of it. And then it's not a statement, an email. It is based on the model. There is a clear, objective way of collaborating based on a common model. And that model is based on observability, right? In fact, I would like to call that observatory. It's a one-step abstraction over the observability data, which is a lot of data. You cannot collaborate on observability data because there's a huge amount of data deluge, right? Similarly, the QA team can feed forward initial findings to SRE, and then SRE or ops can update their playbook and runbook. And as SRE or ops people find some behavioral issues, they can feed it back into the QA, and then QA can in turn feed it back. Nothing prevents SRE and ops to directly talk to the dev. But what is important is they don't send email, or they talk in terms of models. They, for example, they'll say, I have updated the row 55 of the failure model. Failure model in our case, now we use Excel sheet, inspired by failure mode effective analysis taken from manufacturing industry. So, collaborative control system. Now, all three will collaborate on a common, model, right? Next is control system based on life cycle. Now, this is interesting because today, if you look at it, you have process quality indicators, you monitor and report process. You could be branch metrics, it could be change metrics, authorship metrics, DORA metrics. Then you have the structural quality indicators, code quality, and architecture quality we don't even measure today. There are ways and means of measuring architecture quality. And then the product quality, which is in terms of number of bugs or incidents or degradations or whatever, non-functional and functional. The interesting thing today is there is no continuous correlation. There are no leading and lagging indicator correlation. Now, the advantage in having this continuous life cycle control system is you continuously look at what process events and actions are being taken upstream that are causing downstream product quality issues. And then which code is, if you go today, if you apply this code quality tool, you have a bunch of findings. Which ones are significant? So through this continuous analysis, I'll show you a visualization how we do analysis. It is possible to correlate modules A, B, C are very sensitive to code complexity. If the code complexity increases, there is a high chance that production quality will suffer, right? So continuous leading, lagging, and multidimensional control system has to be in place. Now, if you look at this whole diagram, there is a built-in experimentation, built-in traceability, built-in modeling, a synthesis of hypothesis versus experimentation, and a continuous collaborative approach through all the three groups collaborate, and then the life cycle activities are coordinated and correlated. Now, some such, if you look at this, I don't have time to explain to you. You could use a lot of these visualizations, bubble chart and three-dimensional chart, wherein you could look at, for example, if you see this, there are some large red. The size of the circle means that there were burst changes, and the color red indicates that code quality deteriorated. And then you could look at the top lines are actually product quality, your throughput, your build on build throughput and latency change. You could start to visualize how the structural quality is affecting product quality. Similarly, you could do that three-dimensional. Now, what is the takeaway for us is cloud distributed systems are inherently uncertain. We do have observability. Observability is one aspect. We need to build a framework above it. And second is SRE role has to be complemented by upstream activities. Otherwise, SRE role is so comprehensive, so rigorous, so detailed. Many customers say, I will not be able to find one role with all these super duper qualities, right? And what is important is every decision, whether it is a design decision or a testing decision or a SRE decision, every decision must be aligned to the business goals. And this is one of the ways of ensuring that as cloud adoption picks up, as we get into platform economy, our platforms will yield business benefits than ever before.